So next separation technique is paper chromatography. Again, this is a very powerful technique, but paper chromatography is the very basic one. So this chromatography is used to separate dissolved substances. Let's say chlorophyll pigments you want to separate, or uh, what are the different colors present in the ink. If you want to separate that, we use paper chromatography. So we can say it is used separate dissolved substance dissolved substance in a mixture based on difference in uh, let's say solubility, right, and absorption to the paper. So where we use this technique, what are the examples of using paper chromatography? So testing food color, right, then testing pigments, plant pigments, or analyzing the coloring dye, and black ink, right? So these are the method. Steps are very simple, right, and it doesn't require more thing. Paper chromatography is a very easy steps we have done in our previous schools. I mean, if you will recall, you will come to know that this is done. This has already been done actually. So before, let me show you a picture of it before using it. So this is the paper chromatography. Let me show you in a systematic order. Right. So you can see in the steps, first a pencil line is drawn, and imagine pencil line, which is also called start line. You can see here, these are the 4 drops has been done, or right. So you can say draw a pencil line, near the bottom, of the chromatography paper. Why pencil is used? Because it doesn't dissolve in the solvent, but the pigments which are present in it, they will get dissolved, right? This is the first step. Second step, what you do, place small spot of the sample mixture on the line, right? So you can see there is X, and these are the dots. Next, you have to put this paper in a column where the line should not touch the solution or solvent which is present at the base. Solvent is water, so you can say suspend the paper in a container, right, with a shallow layer of solvent. Fine. Ensure that the spot, like excess spot, it must be above the solvent line, right? So this is a note point. Let me write here. Ensure the spot stay above the solvent line. Or the next step. Now what will happen? Let the solvent move up to the paper by capillary action. Let the solvent move up the paper by capillary action. Okay. Next step, as the solvent travel, it carries its component. Let's say this X is consist of A, B, C, D, right? All A, B, C, D have a different solubility, so they will travel based on the solubility component of the mixture at different rates. Those who have less solubility, they will be left early. Which have more solubility, they will go along with the water up, right? So now what you have to do, allow the paper to dry, and then you can see the different color. Allow the paper to dry and observe the separated spot, which is also called chromatogram. There are some note point. Let me discuss about the note point. Like substance that are more soluble, they will be on the top. Soluble in the solvent, travel further or very far, or substance that are more strongly absorbed to the paper move slowly, right? They will go slowly. and the pattern you will get at the end, that's a chromatogram, right? Now let's move to the last part of the topic, that is kinetic molecular theory. So when we talk about this theory explains the physical condition or the physical property of the matter, right? That's very important, that what is the purpose, and you will find that physical properties of matter by describing the particles in the terms of, let's say, motion, energy, arrangement. So when we add these things, like when we see energy, right, arrangement of particles or motion, you will give a very clear idea how the solids are, how the liquids are. So we can say that the kinetic molecular theory explains the physical properties of matter. Means we can say solid, liquid, and gas by describing particles in terms of, what are the term? First is energy, second is arrangement of particles, third is motion. Now the question is, what are the three states of matter? So let's begin with this, where we will discuss about solid, liquid, and gas, and we'll see how. Before, let me show you the arrangement of the particles in the solid. So this is first diagram I want to show. Right, so this is a solid. Let me put it here. Okay, so this is the first state, solid. What we can see here in the diagram, we are seeing that they are very fixed, rigid, right, very defined or arrangement, fixed pattern, right? So we can say that have a fixed shape and volume, right? Then you can see the particles are closely packed. Particles are closely associated or closely packed in a regular, ordered pattern. And particles can only vibrate in place, so they are not moving. That means vibration is there, but they are not moving, they are not free actually. So you can say particles can only vibrate in place. What else? High density, and particles have low energy, right? Lowest energy. If we'll see, if we will see the liquid, right? Let's say liquid sample. The sample is something like this, where particles are there, but there is a gap, enough gap between the particles so that they can move around, they can go wherever they want, right? So they have a fixed volume but take different shape. Shape is not fixed. So we can say have a fixed volume, right? But take shape of any container. You can put in any bottle, anywhere, they will take their shapes. Particles are close, right? But there's a gap between particles. There's no fixed arrangement, so we can say there's a random arrangement, randomly arranged. Particles are randomly arranged. So they have medium density, right? And particles have more energy than solid. Energy than solid, right? But if you see the gas molecule, let's say this is the sample of the gas molecule, right? They are moving in different directions, right? They have very high higher energy, and they can move in any form, anywhere, right? So can we say they have no fixed shape and volume? No fixed shape and volume. Widely spread, particles are free, so they are widely spaced, and again random arrangement, randomly arranged, right? They can move very fast, so we can say move quickly, and randomly in any direction. Very low density, right? And they have very high energy, highest energy among all three states. Now the question comes, is it possible to uh, interchange them? Let's talk about that, right? Change of state. Right? So when we talk about change in state, let me show you one diagram. here we can see that it, that yes, there's a possibility to change all the states, right? So you can see all these melting process, then we have a freezing process, then vaporization, right? Vaporization, or you can say evaporation, better you can say vaporization, vaporizing, right? Condensation, then sublimation, and then deposition. So yes, in all the forms you can separate the things, right? So whenever we talk about the physical state, it's become very straight that we must use, for solid we should write S, for liquid we should write L, for gas we must write G, and for aqueous solution we can write EQ, right? In exams, marks are often awarded for correct state symbol, especially in thermodynamics context. Let's say ionization energy, lattice enthalpy, enthalpy of formations. So this becomes very straightforward and it's being required. Let's talk about what is the connection between temperature and average kinetic energy. Let me go up. So temperature is the measure of what? Temperature is a measure of average kinetic energy, right? So we can say the first point, that temperature is the measure of average kinetic energy, which is also written as EK of the particles in a substance. Fine. What's the unit? So Kelvin. K is SI unit of temperature. So temperature increases, that means average kinetic energy will also increase. So we can say that temperature is directly proportional to average kinetic energy. Temperature increase, higher the temperature, faster the particle will move, right? So we can say higher the temperature, the faster particles move, right? So let's try to understand how they are connected using a graph. So this is the graph. Okay. So this is called change of state graph. Let me write here. change of state graph, right? So let's say this is the first, I'm putting a number, this is first the solid. At this point they are converted. This is the third point, this is the fourth point, this is the fifth point, and the last is the sixth point. So in this we'll discuss about what is happening in the graph. So let's say explanation of graph. So let's start with from 1 to 2 what is happening. So substance is heating up, right? So we can say substance is heating up in the solid state, right? Then particles are vibrating, particles vibrate more, and what is happening when they're gaining the temperature or gaining the vibrations? Heat energy is being evolved, and due to heat, and they gain kinetic energy, right? So what is happening? So temperature increases, right? Now between 2 to 3 what is happening, right? Melting, right? You can see it's melting occur. Energy is used to overcome intermolecular force, not increase kinetic energy, right? So simply energy is being spread. So we can say energy is used to overcome intermolecular force. Not increase kinetic energy. Now what is happening? Temperature remains constant. Temperature remains constant, right? Next, between 3 to 4 what is happening? So between 3 to 4 we can say that the substance is heating in the liquid state, right? Then particles move more freely. Particles move more freely, and they are gaining kinetic energy. Now what is happening? Temperature is now increasing. You can say temperature increases. Now between 4 to 5 what is happening? Can we say boiling? Right? Because boiling occurs, and when the boiling is going on, energy goes into overcoming the intermolecular force. We can say energy goes into overcoming intermolecular force. So temperature remains constant, right? So can we say here temperature remains constant. Now what is happening between 5 to 6? Last stage. Now substance is now in the gas form. It's a gas. Particles move rapidly, right? Particles move rapidly faster, right? And have more kinetic energy and have highest average kinetic energy. And now temperature increases. Temperature increases. So in this way, this graph, the question may be asked in the form of the graph to explain some of the part. So this can be done. Next, we'll talk about how we can convert the unit of temperature, right? Let's say converting between Celsius to Kelvin, degree Celsius to Kelvin, right? So there's a formula K will be equal to degree Celsius plus 273.15, or if you want to convert into degree Celsius, you can write K minus 273.15. These are the majorly used two formula to solve. Let's say question. Let me give you a question. Always remember, room temperature is considered to be 300 Kelvin, right? So I can say here, in many ideal gas problem, right, room temperature is considered to be 300 Kelvin, right? And if you have, so this is the question. So if you have to convert what is the temperature in degrees Celsius, how you will convert? Find this temperature in degrees Celsius. So how to do? So degree Celsius is equal to Kelvin minus 273.15. So it's 300 minus 273.15. This will be 26.85 degrees Celsius. This is the answer. This is how you can calculate. So average kinetic energy depend on temperature in Kelvin, not mass or identity of the substance. So as temperature, at the same temperature, all gas have the same kinetic energy, but lighter gas move faster, heavier gas move slower. So this is the end of this S1.1. Hope you all have made your notes. These notes are strictly based on IB current syllabus. Again, I will come up with the S1.2 in the next video. Keep growing, keep studying.